Welcome to the presentation Is bolt loosening based on advanced pretension functionality predictable? My name is Michael Klein. I'm from INTES, the developer of the FEA software PERMAS. I'm the manager sales and responsible for business development, benchmarks and training organization. Feel free to send me an email for any questions. At the beginning I want to start with a short commercial about PERMAS. PERMAS is making realistic simulations practical. PERMAS is a standard software for thermomechanics, vibroacoustics with built-in optimization. It's a general purpose implicit solver with a broad functionality, high performance for increased productivity is built in the software from the beginning, so that you can use also fine meshes for best accuracy, and it has the best-in-class contact analysis with high accuracy and high speed. We deliver constantly new innovative functionalities in PERMAS for a wide range of industrial application, like you can see here in the pictures on the bottom of this slide. On the right hand side I have a small example. Here you can see a part of a rear axle with gears and tapered roller bearings, and you see the torque load and then the rolling of the gear wheels, and visualized with colors is the stress. Back to the presentation, I would like to start with a short motivation and the objectives, then followed by an introduction of bolt loosening based on the NAFEMS presentation from the World Congress in 2017. I would like to show a solution with a new feature set for bolt loosening. This new feature set is used for a multi-bolt model. I would like to show the loads and results of this analysis, and I will conclude at the end with some final remarks in the conclusions. The motivation for self-loosening is very clear. Self-loosening is typically mission critical. Bolt loose pretension during operation leads to structural failure. So the current understanding of bolt loosening is that a bending is a very important trigger. So we do parameter study based on simulation and show improved possibility to indicate self-loosening by simulation. And with this presentation, the ultimate objective is to develop model technique and indicators to predict bolt loosening in industrial multi-bolt models. So we came from single bolt models. INTES has presented it on the NAFEMS World Congress in 2017, a solution for this based on Juncker test. The Juncker test is shown here on the right hand side, and the main thing is that the bending in 3 mm is done at the bolt head in both directions, ongoing all the test. And we want to go to a industrial multi-bolt model with a simplification of modeling and reduction of runtime per bolt, but we want to keep all physical effects, and with that we want to keep the accuracy. Here is the bolt model from the Juncker test that we have used in 2017. It's only one bolt, and we have an alternating bending load. On the left hand side you see the complete finite element model, but most interesting is the detail of the thread, and we show here in a picture the bolt thread, and this consists of a detailed mesh with a very huge number of elements, like you can imagine from this picture. On this small movie you can see how the simulation is done with an ongoing or alternating bending load. We hide here some element parts, and now you can see that the contacts in the thread area are closed and opening, and so we get this bolt loosening in this model. I would like to show you some results from this Juncker test, and on the left hand side you see the pretension loss dependent on the friction coefficient, and with lower friction coefficient you get faster reduction of pretension. And nearly the same result could be shown by the rotation of the bolt head, and you see the same effect for the rotation of the bolt head here, that you have bigger rotations for lower friction coefficients. So we concluded that loosening could be shown by simulation, and to use this for multi-bolt models we need further developments. We need modeling and simulation effort to be reduced for this type of models, and we want to keep the detailed physics behavior at thread and bolt head so that we have the same effects for the multi-bolt models. So at the beginning I want to show the new feature set for the bolt loosening. So the detailed physics behavior at thread and bolt head are necessary, so we keep that, but we want to reduce the modeling time, so we want to have a cylindrical bolt model, mainly by hexahedron elements like shown here in this picture, that you have a fast meshing, excellent representation of geometry and stiffness, and then we add our PERMAS high accuracy CLF condensed large Lagrange flexibility matrix contact solver to get high accuracy in time. So the basic of this technique is that we don't add to the stiffness matrix additional Lagrangian multipliers. We do a condensation to Lagrangian contact conditions in PERMAS, so we get a reduced, very small system that it's much smaller than the stiffness matrix. So this nonlinearity can be solved much faster in PERMAS. But we want to have a multi-node contact in thread and bolt head area, that we get correct force directions and friction, including stick and slip in the thread area. To make it easier, we have a lot of inputs by parameter. We have as parameter the alpha, the pitch of the thread, we have the pretension force, the friction coefficients for sticking and slipping, and we can also add locally distributed clearance to represent bolt thread quality in each single bolt. For this presentation we use a real model to show you the effects. Included are all mechanical relevant components from the rim to the axle. The support is at the axle, and here are some characteristics of this model. We have a 1.1 million element model with different types of element elements. We have 6.8 million degrees of freedom, 11 contact regions and 22 bolts with pretension in this model. The subject of the investigation are the 5 rim bolts to detect the loosening. We have different loadings, we drive forward, backward, and we have braking. So, typical load during vehicle operation are the driving maneuvers. So forward, backward driving, this is most frequently the general effect on this rim. Then braking as a peak load, and also steering is one part. A little remark, wheel on left and right side all have the same right-handed screw threads, so the effect will be different on left and right side. That can we expect. The loads are acceleration, deceleration and the weight. So for the simulation we use a fixed wheel and rotating load because this is much easier to use for the simulation. Here we used for the simulation 6-degree steps. The contact modeling of the bolt is very easy in this case. We have contact in the bolt head area between the bolt and the structure, and we have contact in the thread area of the bolt for exact threads. So we need for the bolt here only a linear hexahedron mesh, no helix mesh is required, no detailed thread. This is all done by parameters. Recommended is that pitch is used as element height in the thread area, like shown here. And there are no restrictions for all other parts, so all linear, quadratic, volume elements and incompatible meshes are allowed. Meshing as required for good stiffness and geometry representation can be used as usual. So, some additional words to the loosing process. The loosing process in detail is for typical connections. Sliding does not occur in the entire contact area. This will lead to a sudden collapse. But we want to simulate the slow loosening. We have small moving slipping areas which are sufficient to crawl forward in a wave-like manner, like a caterpillar. You see the same effect here in the simulation of a ball bearing, where we can see the crawling effect between the outer and the inner housing, and by the deformation you see when one ball comes after the other. We have this crawling here. You can follow the crawling by this blue line, and you see that the mesh is moving of the inner housing. This nature of behavior is typical for bolt loosening in connection of industrial structures. So we checked the sticking and slipping, here in red the slipping for the wheel rim model and the bolt thread and head area, and you see there is never a complete slipping, but there are big slipping areas from top to the bottom of the bolt thread area, sometimes during the rotation of the wheel. So we can expect loosening. Here you see the global results. At first on the left hand side you see the displacements, again with a fixed reel, and so you see the displacements are rotating, and we check also here the contact friction forces between the bolt head and the structure, and also in the thread area, and we can follow all the frictional forces through the rotation of the wheel to check this. So with the results at the bolt are very important, we check them more in detail. So we get accurate contact results in correct directions, so that it leads to excellent prediction of loosening process in both bolt head and bolt thread. So we see here the contact status in colors by blue sticking and red slipping, and it shows that the loosening is possible. We have large sliding areas on the head and the thread, and several times the area of slipping and the thread extends from top to bottom. And we checked the frictional forces, where especially the frictional direction is important. In thread area, the direction shows a mixture of frictional forces along the helix and down the flank. So it's a mixture effect by slipping here. The loosening can be shown by checking the rotation of the bolt during the simulation. Here is shown the loosening during forwards driving for a friction coefficient of 0.15 and a pretension force of 20,000 for the first rotation. And we observe all 5 bolts of the wheel. So the rotation of each bolt head is indicated for loosening. So we see over the rotation of 360 degree that we have a rotation that is indicated here on the left hand side for all bolts. So the rotation is clearly visible. We have loosening of all 5 bolts, but we have to calibrate this with measurements for quantitative accurate prediction. If we want to check more rotations, here we checked 3 rotations with the same other parameters. We see that the most loosening happens on the first turn of the wheel, and then we have, starting from the second turn, a constant loosening with all subsequent wheel rotations. So we have the same behavior. So you see, for example, for bolt number 5, that the same behavior is repeated for all rotations. If we compare different friction coefficient from 0.1 to 0.3, we can see that the multi-bolt model clearly is able to provide results for the different friction coefficient. So you see the influence of friction coefficient is covered very well by the new bolt model. So you have less bolt loosening with increasing friction coefficient. So note bolt loosening with a very high friction coefficient is shown by this model. The next parameter we have checked is the bolt pretension from 15,000 Newton to 35,000 Newton, and also this model is able to show the influence of the pretension force, and you see that less bolt loosening with increasing the pretension force has happened. So with the highest pretension force we have less loosening than with a low pretension force. So this bolt pretension is also possible to be simulated by this model. And another effect that I want to show is forwards, backwards, or right and left side of your real with the default parameters. We have checked this and we found that for forward driving we have a loosening, and for backward driving we have tightening. So this effect also is part of our advanced model. So let me conclude. We have a model where it's successful, bolt loosening prediction possible with high accuracy. This is based on a new simplified bolt pretension modeling in PERMAS. You get easy, quick modeling, so multi-bolt models for industrial applications are possible to mesh without additional meshing time, and it's much faster than the model with the meshed thread, so also an indicator that it's possible for industrial multi-bolt models. To give you a hint how long it will take, so for this bolt model it takes between 30 and 50 minutes per step, and you remember this was a 7 million degree of freedom model, and the runtime is strongly dependent on the parameters. So with different friction coefficients you will get different complexities of solutions, so the solution time varies also. Very important is that the parametric bolt model contains all important physical parameters. You have pitch and flank angle available, you have friction with friction coefficients for sticking and slipping, you have the pretension force, the clearance, and you have the geometry of the model. So it is easy and directly possible to compare different variants of the same, so you have all parameters, geometry possible, and so you can improve the behavior of your structure. So you get a very powerful tool, and it's fast and easy to use and very accurate for bolt loosening prediction. Don't hesitate to contact me in case you have any question. Please write an email directly to me and I try to answer it as fast as possible. If you need more information about PERMAS and INTES, feel free to check our homepage.